Hello, everyone. All right, so very excited today for our third keynote of L4DC. Today we have the pleasure of Yuanyuan Shi as our keynote speaker. So Yuanyuan is an assistant professor in the Department of Electrical and Computer Engineering at the University of California, San Diego. So her research focuses on machine learning, dynamical systems, and control with applications to sustainable power and energy systems. So her research has been recognized with several awards, including the inaugural Michael R. Anastasio LANL UC Early Career Faculty Scholar Award, the NSF Career Award, the Schmidt Sciences AI 2050 Early Career Fellowship, the Hellman Fellowship, and Best Paper Finalist recognitions at last year's L4DC and ACM E-Energy 2022. So, take it away.
Thank you, Stephen. And thanks a lot for the organizers for the invitation. It's truly a privilege to be here. L4DC has always felt like an academic home for me because my research sits right at the intersection of machine learning and control. So it's a great pleasure to be here and share about our work on neural operator learning for control. My name is Yuanyuan Shi. I'm assistant professor from UC San Diego. So start with, this is a joint work with a wonderful team. The work is led by my PhD student, Luke, who is here, in collaboration with Professor Miroslav Kristic. Pejia was an undergrad in my team, Professor Nikolai Antesnov, and his former student, Shiraz. Thank you all. And the talk will be mainly based on the following three papers, where it represent a good collection of learning L4DC, control, transaction automatic control, and the learning flavor in iClear. So this is the outline for today's talk. We'll start from the motivation, where I want to show you some operators that arise in control systems and where neural operators are. And I'm very happy this morning's oral session actually gave a lot of warm-up on that already. And after that, I'm going to show you three applications of the operator learning for control systems, like in delay systems, in PDE control, and in motion planning. So at the moment, this may seem like three different problems to you. But the fun part where hopefully after the talk, you'll recognize that operator learning can tie them together as a uniform framework. So you're going to see for the expensive computations, it can accelerate it without lose the guarantees you care about. For example, stability in control or optimality in motion planning. So although they're going to be unified by one framework, but for different problems, you're going to notice they have its own challenges, which makes the problem interesting. So now, let me start with the motivation. So we're going to start in easy. So actually, in control system, there are naturally many operator mappings. For example, let's consider the simple linear system x dot equals ax plus bu with the initial condition x0. So we all know the solution of this to this linear system is given by the matrix exponential multiply the initial condition with the convolution of the control input, right? So, but now I want you to look at this problem from a slightly different angle. If you think about what is the input and what is the output for this map, so for this map, we have the input as x0, which is the initial condition of the system. And U of t is a control signal that we have for the past period of t, right? And it maps to the system state. So this is not like a vector-to-vector function mapping, but is an operator mapping in the sense that it takes in a vector, but also a function, and maps it to another vector, right? So for linear system, we're lucky because we have the explicit solution of the operator. However, once the system becomes nonlinear, we do not have an explicit solution. But this operator mapping still exists, right? And this is actually the operator that we're interested to learn for the control of delay systems. So let me give another motivation for the control PDEs. So here is a partial differential equation, kxy, right, defined in this triangular domain. So the PDE is kxx minus kyy equal this lambda multiply k with these two boundary conditions. So again, if we look at it from the input-output perspective, so for different PDE, right, you have a different, let's see, you're given a different PDE to solve. You have a coefficient lambda of y, and then you solve this PDE, and then you get the solution kxy. So this is, again, an operator map, right, that takes a function of one variable, maps to a function of two variables. And this operator, later on you'll notice, is going to be very useful in the control of a heat PDE, a heat equation. So I have named a few like operators, and you can name many more of these operator maps in control systems. So now the question is, why bothering learning them? Why are we interested in learning them? So there are two main reasons in our work. So one is for the speed. So these operators, usually like the solutions of ODEs or PDEs, they're expensive to compute in real time. And with neural operators, you're going to notice through different applications, we can accelerate the speed of compute in online from 10 times to thousands of times faster. Second, the even more interesting thing is we do not give up the guarantees to buy this speed up. Actually, we're going to show with the learned operator, closed loop system under those approximations can remain stable. So if we have something that is fast and also stable, it actually can enable many potential applications that used to be out of reach. For example, here I'm going to share how we apply this, how we leverage this framework to do online predictor feedback for control of nonlinear systems with long delays, and adaptive control of PDEs, where you don't know the system parameters, so you need to estimate the system online and then recompute the control gains. And also online motion planning in dynamics and complex environments. So I hope you're convinced that it's worthwhile to learn these operators. Now the question is, how do we learn these operators? So we approximate these operators using neural operator. I think majority of us have heard about and used about neural networks in various applications. So there are millions of neural network design. Here I take a very simple one. This is a fifth-hour neural network. Right? You have an input vector. It goes through a bunch of linear layers with nonlinear activation, so you get the output also a vector. So neural operator tries to generalize this concept to learn function-to-function operator maps. So there are also many operator design. I'm going to show a bit later, but they could be unified under this three components if you view it. So this V is a functional space, and this U is an input functional space, this V is an output functional space. And in general, it has three components. So we will have an encoder that to encode our function to a finite dimensional space. And then we learn this mapping in the finite dimensional space. And then we have this projection layer back to have the output function back. So, and with the right design, the key goal of neural operator is the discretization invariance. That means we're not limited by how we're going to discretize this input function or output function, but we're being able to truly get the function back that we're able to query at any specific point that we're interested in. So this is a little bit of a theory of a neural operator that we're going to use again and again for getting our control guarantees. So for a moment, you can skip these detailed conditions and look at this bottom punchline here. Specifically, this is saying if this operator you're trying to approximate is continuous, and if the input function space is compact, then for any desired accuracy epsilon that you want to reach, right, for the approximation, there exists a neural operator that can approximate this true operator, this continuous operator, within your desired accuracy for any input function within this compact set, and for any point that you are interested in query for the output function. So neural operator isn't only this abstract diagram and theories. There are actually many realizations of it, as mentioned in several of this morning's hour session. So like on the left, we have the very popular deep operator network, the deep O-net design. So where you can see here is actually a multiplication of two networks, right? So you have the input function go through a branch network to take the input function encoding. And then you have this Y. This is where you want to query your output function int. And this trunk net is try to get a finite set of functional bases to reconstruct the output function int. And then this branch net is learning the coefficient, how to combine them. So you can view the deep O-net as using a neural network to learn this finite number of functional bases, essentially. So on the right, we have the Fourier neural operator. So from the name, you can tell we have the input function, we do Fourier transform, and then we learn in the Fourier space, and then we do inverse Fourier transform to get back the output function. So we're using the Fourier basis. And those two are the earlier like neural operator designs. And since then, there has been many advances. For example, there are neural operator transformers. There are nomad that try to generalize this inner product to nonlinear operations. And this morning, as you mentioned, you can use other bases like polynomial or other type of bases. So with this rich toolbox of neural operators, we're going to take it and look at how we're going to leverage neural operators for the control of delay systems. So many real-world systems are subject to delays, right? You have an autonomous vehicle, there is a camera, it perceives the world, and right now the cars often run some large model like VLA or word action models. The inference could take a few 100 milliseconds or even longer. So that by the time you decide action, the environment will already change, right? May already change. And also in surgical robot or tele operation, there is a human operator and there is a robot, right? They're separated by some communication lags. And we all have the experience of getting in a bad video call, right? So people can talk over each other. And for these high-stake applications, it could be a bit more dangerous, right? If there is delays in the teleoperate of the surgery or a teleoperate robot while wiping your favorite glass case, right? So, and also in power grid, right? There are sensors distributed across a wide area. We're getting the measurements are sending to the control room. And then when the centralized decision is made, it's going to broadcast back to the local actuators. So the delays could be in the sensing and the control. So a controller that works perfectly well in the condition with no control, no delay, right, can have critical performance degradation or sometimes even destabilize the system under a moderate number of delays. So how do we handle this? So here, let's formalize the problem a little bit. So we have the system x dot equals fx u. And here x is our state, f is the dynamics. And you notice here is an input will have a d unit of delay, and kappa is a stabilizing controller under no delay case. So graphically, this looks like this, and time step t, we measure the state, and then we compute our control actions using this nominal controller. However, it takes about d time unit for this action to arrive in the system, right? So even if this controller kappa is stabilizing works well in a delay-free case, it can destabilize the system because we are applying an action that was correct for the past. So how to compensate for this delay? This idea of using a predictor is actually very intuitive. So because our system have delay, right? So rather than using the current state to compute our system's input, right? Why not we make a prediction about the future? And we are interested in predicting where the state will be, right? And the time the delay arrives. So we define that as PT, as a prediction of the state. So if we can have PT exactly as a state and T plus D, right? We can cancel the impact of the delay exactly. So let's now look at this predictor. So the predictor is given by this integral equation. So intuitively, this is saying, so this is my current system state xt, and this is, I'm trying to end up how much the system dynamics will change over this delay window, right? And this is considering all the control have been computed, and now they're traveling in the flight to arrive in the system. And this PT is our prediction of the system state and t plus d. So this integral equation usually have no closed form solutions. So some sort of numerical approximation tools have to be used, right? And when the system is high dimensional, f is high dimensional, is deep, where this delay time is long, right? You need to compute this integral over a long time horizon, which could be very computationally expensive, especially for real-time control, like in high frequency. So that is exactly our motivation, right? So rather than solve this predictor operator numerically, right, we can reformulate this as an operator learning problem and try to learn this mapping. And what is the benefit? So with this approach, right, we can train this predictor operator offline using a large number of data. And once we learn it well, then in the online implementation, we can deploy this predictor operator to make predictions about the future state and every control step, right? If you're doing this at 1 kHz, so you're running this 1,000 times each second, right, to get your prediction of the state, to plug into your controller, and then to decide what kind of control action you should do, right, to cancel out the impact of delay. So let's be more precise. Where this operator takes in as input is xt, which is a current system state, and ut, this is a control signal over this window, delay window of time, right? And what this operator gives us is P of t. This is a prediction of the system state and time t plus d. So the first question is, can we approximate this operator? Because neural operator sounds very magical, right? Can it approximate anything? Specifically, can it approximate well? Here, the solution of the predictor operator, this integral equation. So recall that we just talked a little bit about the universal approximation theorem of neural operators. It has this critical condition. So this operator we try to approximate, it needs to be at least continuous, right? And actually, where we can show is a little bit more. So if your dynamics is Lipschitz, and then this operator, this predictor operator, is Lipschitz continuous, with the Lipschitz constant is determined by the delay length and also the Lipschitz constant of your dynamics. So with this continuity proof in hand, we can now invoke the universal approximation theorem of neural operators and show actually for any state and control trajectories that you're interested in within a compact set, right? Within a compact set. And if users specify certain desired learning accuracy, then there always exists a neural operator, right, that can approximate our original predictor operator, right, within this user desired accuracy. So this is pretty good. But this is not the end of the story, right? Because we're interested in taking this predictor operator and use it in closed loop to give us the state prediction and every single step, and based on that to do our control, right? And our control inject to the system, and then the system moves on. So we're using this again and again in the closed loop. So the natural question is a closed loop system stable under this approximated predictor? So this is our main result, and the result is positive. So this is saying, right, so if you take a training set of your system state and your control trajectories, right, and then for this compact set of training data, then there exists some learning accuracy epsilon star. So this learning accuracy epsilon star will depend on how large your training data is. Actually, the larger the training data is, then the larger this epsilon star will be. And then as long as you train your neural operator within this accuracy bound, then when you start your system state within this region of attraction, which is essentially within the region defined by your training data, then we'll have the closed loop system to be stable. And the stability is, in a sense, is a semi-global and practical stability guarantee. What does it mean? So it's semi-global because we do have this region of attraction, right? So you cannot start your system state anywhere. But this region of attraction depends on our training data. So if you want to make your region of attraction larger, you essentially need to take a bigger set of training data of diverse states and diverse control trajectories, so we can make this region of attraction larger. But this does not come for free, right? So now you have a larger training data. To achieve like a similar approximation accuracy, you will need more data and also a bigger neural operator. That is a price you have to pay, right? So that is the sense of the semi-global. You can enlarge the training data, so you can have a larger region of attraction, but you need to employ a larger model and more data to achieve that. And also this stability, as time grows, right, we're converging to the equilibrium, but we're not converging exactly to zero. We're converging to an epsilon bar around the equilibrium, right? And this epsilon, right, exactly depends on your learning accuracy. The better you learn, like the smaller the bar will be, and the worse you learn, as long as you're within this band, your system is still stable, but you will have some regularization bias. So this is the result tells us. So now let's see how it works out in practice. So to validate our results, we try out this in a 5-link manipulator system. The goal is to track a sinusoid wave, and this manipulator has about 0.5 second delays. And here we can see this blue curve is a desired trajectory you want to track, the sinusoid curve. And then there are two lines here. The green curve is the predictor operator, where we're using some numerical approximation. Essentially, we're using a successive approximation method to get our prediction plugged into the controller. And orange curve here is the neural operator predictor. And we can see both the methods, right, can track the curves reasonably well within epsilon bar. And here, because of the approximation error of the numerical method is better, so you can see it tracks the trajectory tighter. And then this orange curve is a neural operator approximator, right? It's a larger approximation error, so the tracking error could be larger, but it's all stabilized the system. So in return, when using this neural operator predictor, we can accelerate the computation about 100 times faster. So the successive approximation in getting every prediction takes about 100 milliseconds. So you can do control about 10 hertz. And however, the neural operator takes about 1 millisecond to do the inference. So you can control it in much fun resolution, like 1 kilohertz for some dynamic tracking tasks. So here are more results. We're working on still. So there is a ball, like rolling a ball, right? And the manipulator is running some diffusion policy. So considering both the sensing time and the inference time of this diffusion policy is about 100 milliseconds. Because the ball is moving, right? So by the time it compute get the action, the ball already moved away from the original location. So that's why without the delay compensation, you cannot grab it successfully. And on the right, we have our neural operator predictor. And you can see here, because our predictor predict how the system will evolve right after this delay window, and then we can proactively and successfully grab the ball. And we're still working on to have this work on the real robots. So as a summary, in the first part, I present the framework for the first time, right? So we abstract an operator here for the delay system, and then we establish its continuity. So then we learn this operator, and we show it can accelerate the computation for hundreds of times. And then we follow the stability analysis and show the closed-loop system under this approximate predictor have this semi-global practical stability guarantees. And where the region of attraction is in proportional to the data size and the neural network size, and the regularization bias is proportional to the learning error. So our original result was based on the setting where this D is constant, and you know this D. And we have so far extend this work to where you have multi-input delays. For example, you have a multi-robot team or power grid, different actuators could have a different delays, right? So you then need to learn a set of predictors and to compensate the different delays in different control channels. And where you have unknown delays, this D is now known, right? Which is very common in practice. where you have to approximate this delay, and then you also need to predict the future state given the delay prediction. And also time-varying delays. I think there was a talk yesterday on this time-varying delays on the POM-DP case, right? Because the delay can change from time to time if it's a communication channel. Sometimes it's crowded, sometimes it's free, right? So to the time-varying delay case. Okay. So with that, I think that was the first application you're going to see, and I hope you have the framework in your mind already, because next we're going to see how this operator learning idea is going to apply to the control PDE systems and the motion planning, following a similar idea, but then we're going to build more muscles to make the framework generalized to different problems. So we have looked at to compensate delay in time. So next we're going to look at how it works for PDEs that has both space and time. So there are many real-world systems, like in engineering or science, are governed by PDEs. On the left, we have like the thermodynamics, where if someone gets sick in the room, like how the air-bound particles transport around the room. So then you can think about how do you better regulate this building HVAC, so to reduce energy consumption, while make the indoor air quality safe, right? And on the middle, we have the electromagnetic field. This is a project we actually are collaborating with Los Alamos National Lab, try to control the beam inside a particle accelerator, which are governed by the electromagnetics field. And transportation control, actually, if you look at not in the individual car level, but from the macro traffic level, you can describe it as transport PDE, right? If there is some disturbance at the very beginning, you may say this video, right? This disturbance like will exaggerate and later traffic flows, right? So that can also describe by transport PDE. So the control PDE systems are recognized to be very challenging due to many reasons. So here might be a few of them. So first, this is an infinite dimensional system. To solve them and simulate them are usually very expensive. And also for those systems, we usually don't have the luxury to control everywhere, right, in the domain. We often do not only have access to control a few points and also measuring a few points over the whole space. So here we're going to see how neural operator could help solve some of these challenges. So I'll use this as a running example. So this is a heat equation with a destabilizing source term. So let me explain it a bit if you're not familiar with partial differential equations. So here U of t equals to Uxx is a heat diffusion. And this lambda x term is a source term that is like some heat generation keep pumping into the system. So maybe you can picture a data center, like just a row of the data center. We have several server ranks. And each of the servers is running some big jobs, like training a large models. And they're generating heat, right? And of course, the hotter these servers get, the more heat it packed into the system, right? So the hotter this whole server rank will become. So without any control, the system will become unstable because the temperature keeps growing. It's like someone's mailbox, right? During your out of office period. If you don't check any emails, then your unread keeps growing and grow. And here you have this boundary control, right? So imagine you have some air cooling unit that is blowing cooling air, and you can decide what is a cooling air set point and what is airflow rate, right? And your goal is essentially you want to regulate the temperature in this rank, right? Try to stabilize it and to regulate at certain desired temperature set point you hope for. So how do we stabilize this system? A classic method is to use backstepping. The idea is actually quite elegant. So on the left, we have this heat PDE I just showed you with this destabilizing source term. And the idea of backstepping is if we can find a change of variable, right, that can take our original system U to this target system W, with this control input, right? With this control input. And what is nice about this target system, you'll notice, is it's a clean heat PDE, right? Without any source term. So this system is stable. So the key is therefore to find the change of variable and also this control input that makes this transformation hold, right? So where does this transformations looks like? So here is where the name backstepping comes from. So W, the target system, is a backstepping transformation of the original system. So W essentially equals to U minus this Volterra integral with the kernel function and your original system state U. And then the boundary control is actually is also given by this control kernel K. And then you take this integral only at the boundary. So where does most of the magic here is this control kernel K, right? You may wonder where this kernel function looks like. And it has been discovered about 20 years ago for this specific heat PDE. And this kernel function needs to satisfy another PDE. And this may look very familiar to you. This is one I give in the motivation example, right? So it's essentially this kernel needs to satisfy kxx minus kyy equal this lambda is a coefficient, so like what is a heat source, right, with the coefficient multiply k. Defined in a triangular domain with these two boundary conditions. So what you need to do, right, is if you have a new system, right, if you know this lambda, right, then you can solve this kernel design PDE. Then this gives you the control kernel. Then you can solve this equation, right? This gives you the control input that you need to inject at every time step so you can regulate the heat, stabilize it. And if you don't know this lambda, often the case, right, you can use adaptive control. So you have some parameter estimates, give you a new estimate of this lambda and each time step. So now because you have a new estimate, you need to resolve this kernel PDE, right, every time you get a new estimate. So this may sound familiar, right? This is a repeated computation. So what you'd like to do is maybe we can learn this operator instead, right? We can learn this plan to control design kernel. And so specifically, our framework will have two steps, right? The first step is the offline learning stage. So we take many systems, potential lambdas, and then we solve the kernel design PDE, which is a Gorset type of PDE. And this will give you, using some numerical solvers, or some data-driven solvers if you're interested. And then this will give you the kernel, right, for this specific system. And then maybe you solve for 2,000 systems, right? And then you try to learn a neural operator that can reproduce this plan to kernel design operator. This finished the offline learning stage. And then in the online learning stage, right, in the online control stage, right, if we know the system parameter that is perfect, you can just take the system parameter, fit into this neural operator, right, and it will give you the control kernel. And then you take the integral with the system measurement to get the boundary control input and every time step. If this is come from some system parameter estimation, it is also fine, right? You take your current estimation, go through this design operator, and it gives you the current estimate for the control gains. And then you derive the control input and you eject the system. So what is the question? So the first question is, can we learn this operator, right? Can we learn this operator to arbitrary accuracy that we want? Recall that there is a requirement, there is a conditions, right? So we need this operator to be approximate, needs to be continuous. And actually we can show, right, for any system plan parameters, where the parameter itself and its first order derivative are uniformly bounded. Specifically, the parameter is bounded by b, and the first order derivative is bounded by b prime. Then we can show this plant to kernel design operator is Lipschitz continuous. And therefore, with the continuity, we can invoke the universal approximation theorem. And then we can show, right, for all these systems, right, that we're interested in, we can approximate this PDE backstepping kernel to this desired accuracy, right, as close as possible. So here we show some approximation results for two plants, right? On the top, this is a true kernel for one system, and this is the one obtained by the neural operator approximation, and here is the learning arrow. So you see the approximate kernel looks quite similar, quite close to the true kernel. And this is for another plant with a different lambda. This is how the kernel looks like, and this is how the approximate kernel looks like. But again, approximating the kernels is not our end goal, right? Because we're going to take this neural operator and we're going to put it to the controller and compute the boundary inputs repeatedly, right? This is going to be used in closed loop. So are the closed loop systems stabilizing? That is a more important or a challenging question. So how do we analyze this? So with this approximate kernel and the backstepping transformation, this is a target system that we're going to arrive at. So if you still remember, for our exact kernel, right, the exact backstepping will arrive at like a target system, which is a clean heat PDE, right, without any perturbation. So here with the neural operator approximation, we have these two perturbation terms, right? And these two terms are destabilizing perturbations, and they are governed by this learning arrow, because recall here, this k and k hat, this is exactly the approximation arrow, right, between the exact plant to kernel design operator and our approximate operator. So this is bounded by epsilon. So the intuition is the better the learning, the smaller the epsilon, so the smaller the perturbation will be. And the even nicer thing is, as we're regulating the system, right, our system states get smaller, so this perturbation will become a vanishing, right? Will becoming a vanishing destabilizing perturbation. So now it's really a question about robustness, right? So is the target system robust to a small amount of perturbations? And this is our mean result tells us. So remember yesterday's talk, Dicendra's talk, like the control theory can give us the robustness guarantees, and here is the robustness guarantees. So for any systems, right, where your parameters, right, are bounded, right, within the compact set, and there will be certain learning arrow, and this arrow, learning arrow, will depend on both the system plant parameter and the magnitude on its derivative. So as long as your neural operator, right, is more accurate, is within this learning accuracy bound, the closed loop system, we can get a much stronger result actually here, is a global exponential stability, right? So you can see the controlled system, right, converge to zero, right? And this exponential speed, where this m is the overshoot coefficient. And this overshoot will depend on how unstable your system is, and also how large your learning arrow, especially the larger the learning arrow is and the more unstable the system is, this overshoot is larger. But eventually, very quickly, exponentially, this will dies out and you're stabilizing to the origin. So here are some numerics. So again, we look at two systems. There's two columns. So on the left, we have the top row. This is the unstabilized heat equation without any control. And then the medium row here is under the neural operator controller, right? So how does this PD stabilize? And then on the bottom, we see this is a maximum deviation when you use this neural operator approximate gains compared to when you have like the exact control gains. And here is another system, have very similar behavior. The open loop is not stable. The control system under the neural operator is stabilized. So because here we're replacing the solution of PDE using neural operators, and as you know, solving PDE is expensive, so we can achieve like 1,000 thresholds acceleration. So this is even more compared to the ODE case, right? And the closed loop stability is maintained under this neural operator approximate gains. And here, the stability guarantee we get is stronger, so it's a global exponential stability, right, compared to the semi-global practical stability we get in the light case. So as a summary in this part, right, I hope I re-emphasize the point that we have this framework. We establish the operator to be approximated is a plant to the kernel design operator. So it's a mapping from a function of one variable to the kernel of two variables, right? And then we learn the operator. It can accelerate the computation thousands of times. And what is even nice is we have the approximation guarantees. And what is even nicer is when we plug in this estimation into the closed loop, we can actually preserving the global exponential stability. So we did develop this framework originally for the specific reaction diffusion PDE, and the result can be generalized to other type of PDEs. You can imagine like hyperbolic or other type of PDEs. And also it can work for the observer design problem, which is a dual problem with controller design. And also adaptive control of PDE. This is actually our main motivation, right? Because you're getting a system parameter estimate, then you need to resolve this design kernel, right? So where the neural operator gives us the most gains in terms of online computation. And we have also been developing this PDE control gem, which is for the community who is interested in PDE controls to test out different model-based and develop reinforcement learning or new data-driven controllers to benchmark on different type of PDE control problems. So with that, I'll move to the last problem we're going to look at here is for robot motion planning. Perhaps this is the most visual one. In this problem, right, so we have a robot sit in the red point is a starting point. This is the environment, and it aims to reach this goal position. And all this black area is like the obstacles it tried to avoid. So essentially, we want to find the shortest path from the starting point to the goal position while avoiding all the obstacles. So we can write this, we can write to where we just described in the figure as a mathematical formulation. So the goal is we want to find shortest path, right? We want to minimize the total cost of distance, the travel cost, the integral of the total travel cost. And then this tau is the first time that we reach the goal. So that is called the first exit. Once we reach the goal, the task is finished. And the system dynamics here, because we're only looking at motion planning rather than optimal control. So x dot just equals the action you take. And action is limited to this unit length that we're only trying to decide which direction we go, right? Rather than how quick we are moving. So the solution to this optimal motion planning problem is given by this Hamilton-Jacobian-Bellman equation. So intuitively, this value function describes the shortest distance from certain location to the goal position while avoiding all the obstacles, right? And once you have, or maybe you can picture if you have a bar and the bottom is a goal position, then this value function essentially describes the distance, right, from your current position to this goal position. And if you have this value function, right, it's very convenient for motion planning because essentially you can follow the gradient of the value function, right, to reach the final target. So analytically, right, U star is given by this form. And then once you plug in this U star, we actually find this value function need to satisfy this ECNO PDE. So if every point in the map, right, has the same cost, essentially this value function describes the distance from any given position to the goal position while avoiding all the obstacles. And if certain area have a higher state cost, then you'll find the optimal path, try to bend around them, right? Because the slope around those value functions will be higher. So if our environment change, right, if we have a new layout of obstacles, then if that can be represented by a cost function, we essentially need to resolve this ECNO PDE to get our value function. So we can use that to resolve to find the optimal path. So the idea here is very straightforward. So here, instead of repeatedly solving this ECNO equation, right, why not we learn this mapping from this cost function, which represents the obstacle map, to this value function, which defined by the solution operator of this ECNO PDE. So here is essentially our planning neural operator, or the PNO design. So it will takes in the environmental map. Is essentially the layout of different obstacles. So you have a cost of 1 in this free moving space, and then you have a very high cost in this obstacle area because you want to avoid it. And we take the inverse of it as the input. And then as an output, we want to get the solution of the ECNO PDE, right, which is a value function. And a little bit more, we also want it to be generalized to different goal positions. So we will additionally take the goal position as another input. So our final value function will describe the shortest path from any position to any desired goal position while avoiding all the obstacles. So here is our desired property of this planning neural operator. We want it to have resolution invariance because we want to train in smaller maps because it's cheap to generate the data. And then later on, we wanted this operator being able to run the inference on larger maps, which is expensive to solve. And also, we want this operator to generalize across different cost functions. Essentially, there are different obstacle maps, right? If the environment change, we don't need to retrain it. We can use it to predict the value function. And also, we wanted to generalize across different goal positions. So I'm going to show you like how we designed this operator to satisfy these desired properties. So first, the resolution invariance. So what does it mean? So on the top, you see this is a fast matching method. It's a numerical solver of the Keynote PDE. So you see how the solved value function looks like a 256 by 256 map, a larger map, and this is a largest map of 1028 by 1028. And on the bottom, this is a trained planning neural operator that on a very small map, 64 by 64, and later on we run inference right on this larger maps. So this resolution invariance is given to us because our planning neural operator is based on the foreign neural operator architecture. And recall that it learns in the frequency space, so the operator is able to have this resolution invariance as because when we want to query points in the original domain, right? So you do the inverse transform, Fourier transform, so you can query the point, right, beyond the pre-specified number of grade. So, and we can see what is the value of this high resolution, train in low resolution, and then query on larger maps. So here, this is how the time of the numerical solver fast matching method grows. As we're working on larger maps, bigger and bigger maps, the time grows quickly. And for the neural operator, right, the computation time remains rather flat as we move into larger maps. So the computation here could achieve about 10 times speed up. And next, we wanted to be handled different obstacle layout, right? So this obstacle is actually, you should view it as the solution domain of the PDEs because we are only interested in getting the value functions in the safe area for the definition of the value function, right? And then for those obstacle area, those are invalid areas. So we take the inspiration from this domain agnostic FNO paper. Essentially, we have a masking function. This masking function will mask out the areas that are not of interest to us. And then essentially in the obstacle area, this masking function is close to 0. And then in the free space is close to 1. So in the learned planning neural operator, we're going to multiply this masking function inside the neural operator design. So we're only getting the value function in the free space that is within the valid solution domain. So last but not least, we want our planning neural operator to be able to generalize across different goals. And so far, right, we have only focused on the fixed goal. We take the obstacle map and map it to the value function. But what if this goal position change? We don't want to train a different neural operator. That is where motivates us here. So here we know, if V now is the shortest path between any state to any desired goal position, and if this is the shortest path, right, this path need to be shorter than if you pick any random point, right, and then you sum up these two derail paths, right? So this shortest path needs to be smaller, right, or equal to this detour. So this is due to the Bellman principle of optimality. And we cannot hope this planning neural operator that we train satisfying this property by design. So therefore, we try to incorporate it by a hard coding design. So essentially, we take the value function prediction from the planning neural operator and this state and the goal state, and then we take the difference of it and use a deep norm layer. And because of the norm, because this deep norm layer will behave like a norm, so it will satisfy this triangular inequality. Essentially, this deep norm layer is restricting the activation function to be non-active, and then you have positive weights, so it guaranteed to satisfy this triangular inequality. So with all this design, we actually also have a little bit of theory about, I'll be quick about this. So can the neural operators approximate this ACNO PD solution? So we can show the continuity between the cost function to the viscosity solution of the value function. So we can learn this within a desired accuracy. And what is even nicer is when we plug in this approximate value function as a heuristic function in some of the motion planners like A star or T star algorithms, we can guarantee this path, right, we're going to travel will be a gamma optimal path. And this gamma, right, depends on how large your learning error is, and the smaller the learning error, the closer you are to the optimal path length. And also, this is a relative error because we are going to be divided by the magnitude of the value function itself. So we have the approximation guarantee, and in motion planning here, we also have a suboptimality guarantee. So we have tested out this in several different environments, from the 2D city map to 3D indoor navigation to a 4 degree of freedom manipulation task. And here on the left, we can see how the comparison, right, of this planning neural operator compared to other learning methods. Especially, we can see how this design built on top of each other to give us the benefit. So we have the FNO, right? This has the largest approximation error. Here shows the approximation error. And then once you add the FNO masking function design, it generalizes better to different geometries of the obstacle. So you can see the learning error significantly reduced. And further on our planning neural operator, it can generalize better to different goal positions using the deep norm embedding. So the learning error is further reduced. So here on the right, we compare to more learning methods like NT-field, which are essentially based on physics-informed neural network. So overall, compared to existing learning methods, this planning neural operator could achieve up to 50% reduction of the L2 error on unseen goals and obstacle maps. And also compared to the numerical solvers, such as the fast matching method, on larger maps, right, we can achieve up to 10%, 10 times more speed up. And when you employ this learned value function from the planning neural operator as a heuristics into your classic motion planners, it can significantly reduce the node being visited and give you a close to optimal path compared to when you use Euclidean distance, where it does not capture the obstacle information as a heuristics. So as a summary, so in this talk, you see one uniform framework for 3 problems. So here we first abstract the different operators, right, that appears in control of ODEs, PDEs, and the motion planning problem. So we learn this operator mappings using neural operators. We establish the continuity, and then we guarantee the existence of a good approximation, and we show the speed up from 10 times to 1,000 times, depends on the particular problem you're looking at. And last but not least, we show that under this framework, you can precisely analyze how this learning error will play out in the closed loop. And we can establish through different tools, Lyapunov analysis, input to state stability, to analyze the closed loop system remains a property that we care about: stability in control, suboptimality in motion planning. So I want to close this talk by some opportunities and challenges that I have seen in the operator learning for control and planning space. So far, I'll see our framework is still mostly a supervised learning framework, right? So you have some model-based control design, you take it and you generate massive number of training data, you learn it offline, although it's costly, but the hope is when you deploy it online, it can reduce online computation. But this can actually become a huge burden when we look at some more complicated problems, like in the ACNO equation case, once you generalize to high-dimensional manipulators, where if we want to include the dynamics where we're solving a real HJB equation, using this supervised learning framework is not going to scale up. So the question is, how can we reduce the reliance on label supervision and then use some of the self-supervision or pre-trained models to further enable this to high-dimension tasks. And on somewhat a relevant point, I'll say so far we show a lot of benefit of operator learning for control in the acceleration point, right? So we accelerate the control model-based controller design. We achieve some capability that is not achievable, right? Especially for fast real-time implementations. However, a lot of the PDE control problem, there is no known stabilizing, nevertheless optimal controllers, right? So as AI, like research, auto research and discovery becomes more capable, I think a very promising direction is how can operator learning, help us discover new control laws and observers beyond just speed up the existing ones. So if you're more interested in the scientific machine learning or operator learning itself, I'll say the current most of the operator learning design, the output function is really a function space, so you're able to query an arbitrary point with this discretization invariance. However, the input encoding is still pretty rough, so you're mostly taking a fixed discretization and fit it as input. So I think there are a lot of potential in designing more flexible function representations, and also there are early talks in incorporating hard constraints into this operator learning. So there are also a lot of exciting directions in the learning itself. So last but not least, I think this is a general challenge recognized by many talks, right? So learning in closed loop is in general very challenging. So we notice for this delay problem where our prediction of the state is used by the control law, and the control is, so this error keeps building up. So we will require approximation error up to 10 to the order of -4 or -5 to make it really work. Compared to the PDE case, usually like 10% or 1% error already makes the system stabilizing. So this often appears also in sim2real, where if you want to deploy a policy in a slightly different task, right? So in general, I think learning in closed loop, how to make your model works, right, from sim to real, beyond have this distribution shift, I think is a very hard but really, really valuable direction in general. So with that, I hope you take away this one story, this neural operator learning for control, and maybe you have many interesting problems you're working on that you can frame in this language and do the analysis to make it, to accelerate your applications without losing the guarantees. Thank you all the students, all the collaborators and the founders, and thank you all for the listening. Thank you.
All right, thank you for this excellent talk. Let's take some questions.
For the motion planning component, where you're learning the consistent heuristic, which is great for A-star or RT-star, what are the data requirements for that heuristic to start becoming useful for the planning? And what is the computational cost of calling then the neural operator inside the planner?
That's a great question. Thank you so much. I think we have some of the results here, but I'm happy to chat more offline to show the paper. I think the paper has more results. So essentially, in order to learn this operator, as I mentioned, if you want to purely use this supervision loss, you may need to have like over thousands of training samples of the different obstacle maps. Then you have this cost function embedding, right? You solve the ECNOL PDE using the first matching method, right? And then you generate the ground truth value function, so you can learn the operator in that way. And in this work, we also incorporate some ping loss. So rather than the supervision loss, we also add this physics-informed loss of this ECNOL PDE itself. So it can generalize better, right? The learned value function will follow this PDE, so it can reduce a little bit on the data reliance, and also the value function in general behaves nicer. So that is on the data reliance. And on the computation-wise, it really depends on the map you're running on. Actually, this first matching method has been optimized for years, and it runs really quickly. So here's milliseconds. So if you have very small maps, actually it's faster than even run the forward inference on the GPU. But as you have bigger maps, this is not like a very big map, right? If you have a large area, right, and with reasonable discretization, you have larger maps. I think that's where the neural operator going to have more speed up compared to this numerical solver.
Is there any assumption that your testing map must come from the same distribution as your training maps as well?
We're actually, that's a good question. I think in general, if you want your training error and test error, right, to generalize, you don't expect your environment change too much, right? And for example, in these different cases, we will train an operator for this 2D city map, and we will train an operator for this 3D map. We don't have a foundation model that works across different dimensions yet. Right. Thank you.
I'm interested in the first bullet on one of your last slides about supervising neural operators without relying on an oracle to solve the PDE. And I'm wondering, I noticed that the Gaussian equation is hyperbolic and some of your other equations are parabolic. And are there ways to supervise the operator in a hyperbolic equation using characteristics or in a parabolic equation using a variational principle that doesn't require an oracle to solve the PDE, but learns to solve the PDE?
I see. I think those are very interesting idea. I think there has been, in general, like the general terms, people call those unsupervised neural operators, they'll call it physics informed. So you borrow some idea from the solvers, right? For example, the solutions of the the solutions of the kernel function need to satisfy that Gaussian PDE by itself. So if I don't have the underlying data, what is this lambda, what is my map kxy, right? I can just use that PDE, right, as my loss because I know my learned kernel function needs to satisfy that PDE, right? I can use that. And some of the methods you describe, I think, are clever ideas, and you can combine those with the physics equation itself, along with the boundary conditions. But I'll say even those with those physics-informed term, usually they don't work well completely without data. So it can heavily reduce your data reliance, but usually if you have some ground truth solutions, right, this training data pair, it can really help with the performance when you combine with those physics-informed laws.
All right, thank you.
Right, thank you.
I have a question. So in regards, I don't think you talked too much about like how you actually do this function coding for these examples. Did anything non-standard have to happen there? Or do you just kind of use like kind of off the shelf, like, like what basis functions?
Right. Thank you so much. Yeah, I think that is a mean, like kind of most of the neural operator learning today. I know like for the functional embedding, it's kind of very standard. I think if I go back to the like the figure of the depot net, you can see it very clearly actually. So you basically will take this input function, and then you imagine you have a bunch of sensors or have a bunch of discretization points, and then this is how you encode your functions. And similarly for neural operators, so you take this UX, but there is no way the computer can read in a continuous function. So like basically you take some finite set of evaluations. But there are many other ways. Like for example, if you don't want to take uniform samples, right? You can maybe adapt to the function Lipschitz, you sample more when the function varies more. Or you can actually pick some basis for this functional space and then encode it with the coefficient of those, and you can use Gaussian process to encode the functions. Yeah, I think there are many opportunities there, but today, to most of the, I think the function encoding is still kind of in the very preliminary stage. And that is also where we did. Yeah, okay. Thank you.
Any other questions? Yes.
Thank you for the wonderful talk. So I was wondering, can you talk a little bit about the smoothness of the control that's given as output? So if, in many applications, you will need a piecewise linear or a discontinuous control as an output. And how well do these neural operator approaches, how well do they do in those kind of scenarios?
I see. So in our case, for the operator, you want to approximate itself. You need to establish this continuity of the operator so that you can guarantee like the neural operators can approximate this design operator. And so I think that is kind of the fundamental, the theoretical requirement if you want to preserve both approximation and closed loop guarantees. And of course, if your problem does not satisfy these properties, I think in general in computer science or learning fields, there is nothing stop you to still trying out, but you may not be able to get